Alrighty, let's get back to the second part of this. Laplace of, we already talked about all of this. I don't know what I said that my ALEXA is going crazy. Alright, so Laplace inverse of e to the negative as f of s. The way we figured that out is by taking Laplace inverse of just the f of s itself and applying a shift of t shifted by t minus a, and then multiplying. Absolutely make sure to multiply by u of t minus a. I have in the past students who did not multiply by u of t minus a at the end, and I take off a big chunk of points if you don't do that, okay? So be forewarned. Let's solve some problems. Does this look like Laplace inverse of e to the negative as f of s? Nah, not right away. Right? It doesn't look anything like e to the negative as f of s. What if we were to do this? We were to expand that, distribute that 1 plus e to the negative 2 as the quantity square out, or FOIL that out. We get this. And now can we split this into 3 separate fractions? Yep. Now at least the second and the third terms, do they look like e to the negative as f of s? Yep, they do. Alright, the first one, 1 over s plus 2. Straightforward. The Laplace inverse of that is e to the negative 2t. Okay, now let's focus on this guy. What should we do apparently? Look at this as e to the negative as f of s. What is f of s? 2 over s plus 2. What is a? Positive 2. Are you okay with that? E to the negative as. I'm just comparing e to the negative as f of s with this one, or rather this with that. With a being positive 2, f of s being 2 over s plus 2. Cool. Look at this side. To figure that Laplace inverse, we need to figure out Laplace inverse of f of s itself, which is Laplace inverse of 2 over s plus 2. And then be sure to apply the shift t shifted by t minus a. A is 2. Cool? So that takes care of the first part of it. And the next part is straightforward. You just multiply by u of t minus a, in this case u of t minus 2. As simple as that. Cool? So what about this guy? Well, it also looks like e to the negative as f of s. A happens to be 4 here. F of s is 1 over s plus 2. So would you agree? All we need to do is find the Laplace inverse of 1 over s plus 2, apply a shift of t shifted by t minus 4, and multiply by u of t minus 4. That's it. So this plus this plus this, right? The first one, like I said, is simply e to the negative 2t. And here, Laplace, what in the world happened to this? Man. How am I supposed to know it would do something like that? Okay. Hopefully it won't do that now. Sorry about this, guys. Again? What? It's all supposed to be on just one line, like that guy. this, man. Now? Oh, brother. Maybe let me save that and see. Sorry about that. Yeah, let's grin and bear it. Supposed to have fixed it. I don't know what's going on. Maybe I'll give one last try. Try something else. Scoot that guy. Scoot this guy also. Oh, I'm doing the wrong thing. What an idiot I am. I'm supposed to fix this guy. Okay. This should fix it. Save this guy. Ta-da! Yeah. Okay. Laplace inverse of where the heck are we? All right. We needed to find the Laplace inverse of this. Okay. Does this look like Laplace inverse of e to the negative as times f of s? Yep. F of s is 2 over s plus 2. So Laplace inverse of that f of s, but we apply a shift, t shifted by t minus a, in this case, t minus 2. Be sure to multiply by u of t minus 2. This is what I'm talking about. Right? Failure to do that will result in a few points being taken off. Cool. What do you think about the second guy? Laplace inverse of 1 over s plus 2, shift applied, t shifted by t minus 4, multiply by u of t minus 4. That's it. And that's what results as 2 over s plus 2, 2e to the negative 2t, right? And we'll apply the shift, multiply by u of t minus 2. 1 over s plus 2, e to the negative 2t, apply shift. E to the negative 2t plus 2e to the what? I'm just replacing t with a t minus 2 in this guy. That's it. Okay, times u of t minus 2. Same thing, I'll replace a t with a t minus 4 here, and we get that. That's it. Right? I think this is fairly straightforward. Once you understand that form, what Laplace inverse of e to the negative as f of s, how to interpret that, this is piece of cake. Okay, now I want to show you some graphs. This is going to be very helpful for all of you engineers who would be doing control systems. And who does control systems? Mechanicals, electricals, and chemical guys. Civil people don't do a whole lot of control systems, but that's okay. I still like civil guys. But in control systems, you will see certain graphical things. You want something to behave this way. And so you just have graphs. How do you get an output based on that looks like this? this graph. So for all things like that, you need control systems, and you need Laplace transforms, and you need to figure out Laplace transform of some of these kinds of graphs, right? All right. If my graph of f of t looks like this versus t looks like this, have I already told you that u of t minus a is a graph that looks like this? 0 between 0 to a and 1 for t greater than or equal to a, right? I could have had a circle here and a solid dot there, but you get the picture. Got a question for you. Can you tell me what the graph of f of t times this u of t minus a would look like? I'll check that out. That's a real good question. I gave you the graph of f of t, gave you the graph of u of t minus a. I'm asking you, how do you get what does the graph of f of t times u of t minus a look like? As simple as this. You go to every single t value and look at what u of t minus a is for that t value, and also look at what f of t is for that same t value, right? At 0, this is 0, this is some non-zero value, doesn't matter. 0 times whatever this y value is, right? That is just 0. Okay, scoot a little bit to the right and come to some t value here. This u of t minus a has a 0 value, so 0 times whatever that is, it doesn't matter. As long as it's a finite quantity, which it is, we get 0. So wherever u of t minus a is 0, let me repeat that. Wherever u of t minus a is 0, the product of u of t minus a times f of t would also be 0, right? So the graph of f of t from 0 to a, that just becomes, take that and just make it into 0. Cool. That's how the product would look like on the interval 0 to a. But now let's focus on a itself. At a, u of t minus a has a value of 1. And whatever the value of f of t is at that same t equals a, we just multiply that by 1. So that means our y value in the product would still be this same y value here. Did you get that? Because we are multiplying by 1, this f of t value at times 1, we just get the same f of t value. And similarly, at every other t greater than a, we would just be multiplying this f of t graph by 1, and we would get the exact same graph. In essence, the product of these two things would be on 0 to a, just 0. On a to infinity, whatever this graph looks like, f of t graph looks like from a to infinity, that's exactly how this graph would look. Like that. This is exactly the same as f of t graph on the interval a to infinity. Cool? That's how this graph looks. Get it? Cool. I have a few more questions. Next, I'll show you the original f of t graph and the f of t times u of t minus a graph that we just got. Cool. Now I have a question. What does the graph of f of t minus f of t u of t minus a look like? From the top graph, if you subtract this bottom graph, what would the resulting graph look like? Any ideas? Well, on the interval 0 to a, from whatever these f of t values are, what would you be subtracting? Yeah, that's all 0, nothing. So, would you agree, whatever this graph looks like from 0 to a, even in the subtracted one, the final product, that graph would look exactly the same? Because we are subtracting 0, folks. Now on a to infinity, what are we subtracting? And whatever these values are, minus whatever these values are. But they are exactly the same. So that means on a to infinity, it flattens out. You get 0. So this is how the graph looks like of f of t minus f of t u of t minus a. Cool? All right. I hope logically this is making sense to you. You really need to make sense of it, okay? Now, I start with this graph, f of t u of t minus a, okay? And then from this, if I were to say the graph of f of t u of t minus b should look like that, would you agree with that? What? F of t u of t minus b. What did f of t u of t minus a look like? Where did we wait a minute. How did the graph of f of t u of t minus a look like? Whatever was greater than a, whatever the graph of f of t looked like for t greater than a, that's what f of t u of t minus a looked like. Let me repeat that. The graph of f of t u of t minus a is the graph of f of t on the interval a to infinity, right? On a to infinity, this is the graph, and that's what you're seeing here. In the same way, what is f of t u of t minus b if I were to say instead of a? Then whatever is the graph of f of t from b to infinity. So b, let us say, is somewhere over here. B to infinity is just this sort of flattish portion. That's what I'm showing here. Cool? So f of t u of t minus a is this graph. F of t u of t minus b is this graph. Question. What if I were to subtract this from the top? F of t u of t minus a minus f of t u of t minus b. Would you agree? You would have all of this, and when we get to b, we are subtracting equal quantities, so you get 0. So the graph should look like this. F of t u of t minus a minus u of t minus b. All my struggle was to get to this final point. Cool? Now look at this one. The original f of t looks like this. Then the graph of f of t u of t minus a u of t minus b is the same graph, the graph of f of t from a to b on the interval a to b. How does it look? Whatever it looks like is this graph, is the idea. You want to get f of t u of t minus a minus u of t minus b. You pick the graph of f of t on the interval a to b. That's what you get. Right? So, let's keep this in mind, and I'm going to show you. The important point to note on this graph is, given a function f, define a new function g on the subinterval. Oh boy. All right. So the main point I'm trying to make is, this is useful in writing piecewise functions using step functions. That's the idea. Excuse me. Piecewise functions, we can write them as step functions apparently. And for that, a couple of concepts I need to first go through. U of t minus 0. Any thoughts on what u of t minus 0 would look like, the graph of that, or what it means? Especially when I tell you that u of t minus a, the graph would look like that. By the way, this is a. Can you tell me what the graph of u of t minus 0 ought to look like? Oh, from 0 to a, we should have 0. 0 to a. But a is 0. Okay, so from 0 to 0, you should have a value of 0, and beyond a should have a value of 1. 0 to 0? Oh, that's just 0. So immediately at 1, it would jump up to 1. That's what it is. So so this is how u of t minus 0 would look like. Well, what does the graph of 1 look like? Exactly like this. We are talking about t being greater than or equal to 0. So what does that mean? It means u of t minus 0, ladies and gentlemen, is exactly equal to 1. That's the point. U of t minus 0 is just nothing but the same as 1. Cool. Now, let me ask you, what is u of t minus infinity equal to? Oh, looking at u of t minus a is apparently infinity. And so u of t minus a graph is 0 from 0 to a. Okay, so from 0 to infinity, this would be 0. At infinity, it will jump up to 1. What? At infinity, it will jump up to 1. That means it will never jump up to 1. It will stay 0 all over. In other words, that's exactly the same as 0. Isn't that cool? So u of t minus 0 and u of t minus infinity are special cases of just 1 and 0. That's it. We'll need all of that. Look at this piecewise function. On the interval 0 to 1, look at what I'm saying here. If you know some function f defined on some interval, and you want to get g that is defined on a subinterval ab of that I, f is defined here from 0 to infinity, started at 0 and goes all the way up to infinity. But on the subinterval 0 to 1, it's defined by t square, right? So what this is suggesting is we can write this portion of it as t square, the f of t part, u of t minus a is 0, minus u of t minus b is 1. Check that out. This piece of that curve, this in the piecewise function, this portion, we can replace that with t square times u of t minus 0 minus u of t minus 1. As simple as that, folks. Cool. Now, what about this piece of the curve defined on the subinterval 1 to 2? 2t, whatever f of t is, which is 2t here, times u of t minus 1 minus u of t minus 2. Cool? The first value, u of t minus 1, minus the second value, u of t minus 2. And this 3 times u of t minus what first and second value? Could we think of this as 2 less than or equal to t less than or equal to infinity? Yeah. So u of t minus 2 minus u of t minus infinity. Okay. So the first piece, like I said, is t squared u of t minus 0 minus u of t minus 1. The second one is 2t times u of t minus 1 minus u of t minus 2. And the last one is 3u of t minus 2 minus u of t minus infinity. But u of t minus 0, we can replace that with a 1. U of t minus infinity, we can replace that with a 0. That's what I did. Cool? See, that's the beautiful thing. We can write a piecewise function using unit step functions. But why do you do that, man? Because we can now take Laplace transform of this. Oh, okay. I don't know. Why should we do that? Or why should we learn to do this? You guys in doubly, or even engineers, other engineers. When it comes to electricity, like DC current, how does DC current look like? Just a flat, like our unit step function that we have here. The moment you flip a switch on, a certain constant amount of voltage would be flowing in, or current would be flowing. So that's how a DC current would look like. But then there is also some kind of a ramp input, which means the current will keep on increasing. You can apply an input like that. You can apply a parabolic input, meaning the current would increase in a parabolic fashion. And what you want to do is you want to see the response of a certain system when you apply these different kinds of voltages. For a certain interval, you apply direct current, some constant current. Then you apply a ramp input, something that grows linearly. And then you apply a parabolic. So that is nothing but a step input like this, a piecewise function. There is not a single value of voltage that you are applying to this system. You are applying for a certain period, certain interval of time. You are applying one kind of a voltage and different kinds of voltages at different periods of time. And you want to find the response of a system like this. This is not just a hypothetical thing that I'm talking about. You will do these kinds of things pretty soon. So please pay attention to this and learn this one. Okay? And perhaps keep these notes somewhere nicely stacked up, because you will need it at that time. Okay? All right. Well, I've already taught you how to take Laplace of these things, right? For example, 2t times u of t minus 1. Does that look like f of t, u of t minus a? So you know exactly how to take the Laplace of it. So what I'm going to do is I'll give you a function like this. And I will ask you to first write this in terms of a unit step function like this. And then take the Laplace of it. I will definitely ask you problems like that. They are my favorite problems. And believe me, it's for your benefit I would be doing that. Okay? All right. Theorem, derivatives of transforms. Laplace of t to the n times f of t is negative 1 to the n d to the n dsn of f of s. And n is any natural number. Okay? Let's see. What is Laplace of t square cosine t? Maybe I'll just go ahead and talk about this concept using some example problems. Laplace of t square cosine t. Does that look like t to the n f of t? N is equal to, good, 2. F of t equals cosine t, good. According to the right hand side, what do you think we need to do? N is 2, so the first part, negative 1 to the n, becomes negative 1, the quantity square. D square, ds square of f of s. What in the world is f of s? Laplace of f of t. What is f of t here? Cosine t. You see how simple that is? That's the idea. Pattern recognition, folks. Math is just nothing but pattern recognition to a large extent. So t square f of t, d square, negative 1 square, d square. Negative 1, the quantity square is just 1. Laplace of cosine t is s over s square plus 1. And we need to take two derivatives of this. First derivative, when we take that, I'm applying quotient rule, low d high minus high d low over low low. And so low, the denominator, times the derivative of the high, which is derivative of the numerator, minus high d low. High is the top, s. D low is the derivative of the bottom, which is 2s. That's what I have. Over low low. Low low is the square of the denominator. So that is when we take one derivative. So I reduced the second derivative to the first derivative because I've already computed the first derivative here. Now we need to differentiate this again with respect to s, but before we do that, let's reduce this. See if we can simplify this. Yeah, we can write this as s square plus 1 minus 2s square, which reduces to 1 minus s square. Now apply quotient rule again, and we got the denominator times the derivative of the numerator minus numerator times the derivative of the denominator. That's what I did. And if I simplify, I'll let you go through it. You simplify and you get this. Cool. You might want to pause there and convince yourself that my algebra is all right. Okay. How about this guy? I'm sorry. Looks like allergies are beginning to bother me. Okay. Whoa. Does that look like Laplace of t to the n f of t? Yeah, it kind of does. We can think of it as t to the 1 times the rest of it is f of t. Right? Okay. I wonder if... I do have it. Good. There's no problem in looking at it this way, right? Is there another way of looking at it? We can look at it as t times f of t. Is there another way that we learned about? We could look at it that way. What about e to the at f of t? A is negative 3. F of t in that case is t times cosine 3t. So we could look at it that way. Right? What's that American expression? There are more than one ways to skin the cat. So solving this problem, we can apply either method. So which one appears to be an easier way? Well, if we were to do this, we need to figure out Laplace of e to the negative 3t cosine 3t first, which is not very difficult, but yeah, it's good. And then take the derivative of it. So we would be taking the derivative of something that is a tad more complex, right? On the other hand, here what should we do? Oh, we will have to apply a shift, s shifted by s plus 3. The e to the negative at thing will cause us to apply a shift, s shifted by s minus a, or s shifted by s plus 3. To what? To the Laplace of t cosine 3t. But Laplace of t cosine 3t, oh, that involves a derivative. That's not a big deal. This is a derivative of a simple cosine 3t as opposed to a derivative of e to the negative 3t cosine 3t. So, they are both equally likely, equally possible, but this, I think the second one is just a shade easier. So I would probably use that. Laplace of t cosine 3t, to which a shift would be applied. Applying a shift is just simply replacing s with a s plus 3. That's an easy concept to do, right? So negative d ds t times -1 to the n, -1 to the 1 is -1. That's what I have. D to the n dsn is d ds of Laplace of cosine 3t is s over s square plus 9. And of course, let's not forget to apply the shift. And this again, quotient rule, shift. That's it. Very, very nice problem. Very likely to ask you a question on this also. Cool. Ladies and gentlemen, that's it. So I told you what problems you are responsible for in this. So please be sure to work on all of them, as many of them as you need to. If I were you, I would do all of them. And if you have any questions, please do not hesitate to contact me and let me know. I'll gladly work those problems out for you. Alrighty.